we are looking at the boundary layer equations. And for boundary layer, what we said was these equations are valid for large Reynolds number flow. And this we are talking of 2D steady case. And our equations are du by dx plus dv by dx y is equal to 0. So these equations are what are called the boundary layer equations. In some set, you can think of these as a subset of the Navier-Stokes equations. Now, also what we know is in the boundary layer, u is equal to u of xy, v is equal to v of xy, but p is equal to p of x. And the equations are valid in the range 0 is less than y is less than delta. And so I'm just repeating this so that you understand what we are talking of when we talk of this beast called the boundary layer. Okay. And then beyond y is equal to delta, the potential flow solution is valid. In potential flow solution, we know u of xy, v of xy, and we also know pressure also as a function of x and y. For the potential flow is something which, when we start the boundary layer solution, we know the solution. But now what we have done is we have divided the region into two zones, a boundary layer and a region away. And in the boundary layer, the the solution, the equations are slightly different. The potential flow solution basically, and if you look at physical quantities, viscosity, effects, important in boundary layer and negligible outside. And similarly, if you look at vorticity, it's significant in boundary layer and it is negligible outside. Why do I say this? Because we are talking of potential flow, which are irrotational flow. And the pressure P of x in the boundary layer is found from potential flow solution of Pxy. As we know that in the boundary layer, pressure does not change with y. So whatever is the potential flow solution at the edge of the boundary layer, that can be used to find pressure in the boundary layer. Now, using this, a methodology was developed for boundary layer flows, and let's discuss the general boundary layer methodology. And we are talking this for, again, 2D steady flows. But we will make now, we'll assume that the surface, so when we have flow past a surface, this is a curved surface. And what we do is we define body fitted coordinate. So x-axis is along the body or the is along the surface. This coordinate we will call as x, and y is locally perpendicular to x at each x. So even if the surface is curved, we have a curved coordinate. So x-axis is like the stream-wise coordinates, or which you may have also seen as the path coordinates, and y is the normal coordinate. Now, what is y is equal to 0? What is represented by y is equal to 0?
So body surface.
It is the body. It represents the surface or the wall. Y is equal to 0 gives us the equation for the wall, which is only a function of x. Okay, so that's what we get, and x and y are defined like this. Now, in this, now let's make some notations. We define in boundary layer terminology, capital U of x is defined as the potential flow velocity at the wall. Whatever the potential solution you get y is equal to 0, we call it as capital U of x. Now let's try to see what is capital U of x. What does this mean? So if this is the wall and this is what we call as the x, now potential flow, can you have, or when can you have a y component of velocity at the wall? Can you have a y component of velocity at the wall? What is your guess?
No, sir.
Pardon?
So it should be 0.
It should be 0. So now, when I have asked the question when, so that means normally Vy, that means the potential component, not at the wall, must be 0. Why is Vx not 0 in the potential flow? If I'm talking of potential flow, can Vx be non-zero at the wall? Please answer. In a potential flow at the wall, just at the wall, can the velocity be non-zero? In a viscous flow, we know it has to be zero. What about potential flow? Am I connected? Am I with you or no?
Yes, yes.
हाँ तो बताओ, पूछो थोड़ा. अगर पोटेंशियल फ्लो वॉल के पास है तो वॉल पे वेलोसिटी नॉन जीरो हो सकती है क्या? Can the velocity be non-zero at the wall?
I think it should be zero.
See, it will be zero if it is viscous flow. In inviscid flow, we relax the no-slip boundary condition. So Vx at the wall can be non-zero. But Vy is equal to zero if the wall is non-porous. And this is what we did in potential flow theory, that we relax one of the boundary conditions and we relax the no-slip boundary condition. But the normal boundary condition, irrespective of whether it is viscous or inviscid, the velocity has to be zero if there is no porosity at the wall. Okay? Is this point clear?
Yes, sir.
Yes, sir.
Does everybody? Now let us look at something. So now, if we apply Bernoulli equation at the wall for the potential flow. Now, for potential flow, we can apply Bernoulli's equation. We can't apply it for boundary layer flow. But in the potential flow, if we apply boundary layer equation and let the pressure at the wall for potential flow be given by capital P of X. That means on this wall, I have potential flow, and then at any X location, I call the pressure as P of X and the velocity as capital U of X. Obviously, these are only functions of X because we are talking of values at the wall. So Bernoulli equation will give me P of X plus half rho capital U square is equal to constant. Is this fine?
Yes, sir.
So now we are not talking of the boundary layer flow, we are talking of potential flow. And for potential flow, we use these symbols capital P and capital U. Let us differentiate this with respect to X. And you will see why I am doing this. When I differentiate with respect to X, I get dP by dx plus rho U times du by dx is equal to 0. And this leads to minus 1 over rho dP by dx is equal to U du by dx. Or so now I'm not explicitly putting x in bracket after u, but we understand u is a function of x for a general case. Now you see what our logic was. This is the wall. This is the boundary layer. And what we say is, this is x, this is y. And partial P by partial Y is equal to 0 in the boundary layer. So whatever is the potential flow solution here, the same pressure will continue, it will not change up to the wall. So that means what we can do is, in the X momentum boundary layer equation, our equation was U partial U by partial X plus V partial U by partial Y is equal to minus 1 over rho dP by dx plus nu d2u by dy square. We can replace minus 1 over rho dP by dx by first minus 1 over rho dP by dx and then by u du by dx. So that means the X momentum equation, X momentum boundary layer equation, this becomes capital U du by dx plus nu d2u by dy square. And in this way now, capital U is known from the potential flow. And of course, the second equation we have is the continuity equation. Now there is no equation for pressure because we have replaced the pressure term with the potential flow velocity. And the boundary conditions we have is at y is equal to 0, u is equal to 0, and v is equal to 0, and as y is equal to delta, u is equal to. Now, at the boundary layer edge, we say u is equal to, and what we do is we put it equal to capital U of x because the boundary layer is thin. So here if the velocity is capital U of x, when we traverse across the boundary layer, the velocity, the potential flow velocity will not change too much because potential flow is an inviscid flow. So the velocity gradients are low there. So therefore, at y is equal to delta, we put in the condition that small u is equal to capital U of x, and this is because delta is small. So replace u of x comma delta by capital U of x. So basically this delta we replace by 0 because the potential flow velocity will not change too much. So these are our equations. Now, this is what in 2D. If we use now, because our coordinates are not straight, they are curved. Then if we use curvilinear equations and derive the boundary layer equations for 2D flow, they will turn out to be the same as for Cartesian XY equations derived above, provided radius of curvature of the wall is much bigger than the boundary layer thickness. That means if radius of curvature is large, we get same equations in curvilinear coordinates as for XY coordinate. coordinates. So the boundary layer equations will not be the same if we talk of flow past a needle. If it is a needle tip, then obviously radius of curvature there is much large. But if we are talking of a curved wall, which is a gently curved wall, then we will get the same equations. The extra terms, see, in curvilinear coordinates, we realize we will get extra terms. But the extra terms, and this you have seen even in the cylindrical coordinates when we write the equations, we get some extra terms. The extra terms in the curvilinear equations are of the same order as the neglected terms in the boundary layer equations, provided radius of curvature is much bigger than the boundary layer thickness. And so example cannot apply boundary layer equations flow past the tip of a needle, because there the radius of curvature will be very small. Now, if you look at the boundary conditions, let's look at the boundary conditions. The boundary conditions we have said is at y is equal to delta, u is equal to capital U of x. But here there is a problem. Can anyone tell me what is the problem in writing the boundary condition like this? If I use this boundary condition, y is equal to delta, u is equal to capital U of x. I'm claiming there is a problem. Can anyone tell me what the problem is?
So delta is not a constant.
Delta is not known. Delta itself has to be derived. And the problem with this is delta is unknown and has to be solved for from the boundary layer equations. So that means this is a problem. Now, so this boundary condition will not work. So what do? So here what we do is, again, we normalize the y coordinate and we shrink it because it is as it is, we normalize as it is shrunk as compared to x. So what we do is we put y star is equal to 1 corresponds to y is equal to delta, x star is equal to 1 corresponds to x is equal to L. So we can see in the y direction things are shrunk. But because delta is much smaller than L, we place the delta in the boundary condition by y is equal to infinity. So the second boundary condition used is as y tends to infinity, small u is equal to capital U of x. So that is how one solves it. And this is to follow more of this. This is what one does in asymptotic analysis. Our y coordinate is very shrunk as compared to x. So when we talk of going very large distances in y, that means we will still be of order 1 in the x direction. So that is why we shrink it. And they also you will realize there is an apparent conflict, because on one side we are saying delta is small, so we replace u by capital U of x. And then what we do is, we instead of saying delta, we replace this delta by infinity in the boundary condition. But this is all a part of how asymptotic analysis are done. So the final boundary layer equations and boundary conditions are, the equation is first the continuity equation, and then the momentum equation, and then the boundary conditions as y is equal to 0, u is equal to v is equal to 0, and as y tends to infinity, small u is equal to capital U of x. And if there is a porous wall, then the boundary conditions are at y is equal to 0, u is equal to 0, and v is equal to velocity at the wall. Now instead of 0, this is the porous velocity, and as y tends to infinity, again small u is equal to capital U of x. So this is how, these are the boundary layer equations, and this is the methodology we will use to solve them, where capital U of x has a special meaning. Okay, is this sort of scheme clear to everyone?
Yes, sir.
All of you are fine with this? So then,
Yes.
so given this, now let's look at the case of boundary layer on a flat plate. Now, when we talk of boundary layer on a flat plate, uh, how are we going to find a flat plate in a potential flow? How will, so because basically we need the potential flow solution. So first we have to see how to find flat plate in potential flow. Any answers? So let us say which will be represented by the x-axis. So how do we find this? We look at streamlines in a potential flow, and if we get a straight streamline like this, if we get a streamline like this, which is parallel to the x-axis, then we can replace the streamline or a part of the streamline by a wall. So let's say if this is the flow, we'll just put a part of this and we say this is the wall. This is how we find flow past bodies in potential flow. Is this clear?
So in the case of porous wall, then also this will be valid.
So in case of porous wall, you will have to then find, uh, porous wall will be slightly more complex, because then you have to find a potential flow, which gives you a v component of velocity at the porous wall.
Yes, sir.
So you'll have to find some sort of a flow past porous wall. Okay. So there, in case of a porous wall, what will the potential flow solution look like? That would be a, I'm sure we'll be able to find some potential flow solutions like that, which also treat a porous wall. But what I'm saying is, in any flow, if you find a streamline which is parallel to the x-axis, that will represent that flow past a flat plate. Okay, so now the case one which we look at is, which is the most common case, boundary layer on a flat plate with uniform flow at infinity. There can be different cases which I will show you in a minute or by the end of this lecture, that there can be other flows which represent flow past a flat plate. So if we have a potential flow with stream potential given by phi is equal to u of x, then here the streamlines in this flow, if you plot this, you have done in your first course, streamlines for uniform flow for potential flow look like this. This is whatever is the velocity capital U, which is uniform. Uniform means it is constant, it's not a function of x. And then what you do is, in this flow, you say this streamline is a body, is a flat plate. So this is how you get flow faster flat plate, which is uniform at infinity. So in this flow, so we replace part of the streamline with the solid body. So this potential flow is what gives you uniform flow past a flat plate. So in this flow, capital U of x is equal to a constant, which we can call it as capital U. Now it is not a function of x. So therefore, now in this, what will be u du by dx?
0.
It will be 0 because capital U is a constant. So this is sometimes also called as ZPG flow. What is ZPG? Zero pressure gradient. So in this flow past a flat plate, we have this, and the equation becomes u du by dx plus v du by dy is equal to nu d2u by dy square. So this is the boundary layer equation for uniform flow past a. Okay. Now, just now I told you we can find other potential flows also which represent flow past a flat plate. But these will be not uniform flow. So that is the difference between these flows and the one described earlier. And the example is, let's look at source flow. This once again you have seen in your undergraduate course. You have a point source at origin. For such a flow, the stream function phi is given by q log r, and stream function phi happens to be q theta. Yeah, that's it. So if stream function is like this, v sub r is equal to q upon r. And how do the streamlines for a source flow look like? If this is the origin, how do the streamlines look like? Any idea?
So radially outward.
Radially outward. So streamlines are going to the potential flow solution. These will be the different streamlines. So what we can do is there's a streamline like this. I can replace a part of this streamline, replace the streamline y is equal to 0 by a solid body. Now for this flow, let us try to understand. If we replace it and we want to talk of boundary layer on this flat plate, what is capital U of X for this flow? Can we try to find this? So let's see how to find this. In potential flow solution, the velocity for a source flow is given by, there's only radial component VR ER, and this will be equal to 1 over R partial phi by partial R. So this becomes equal to Q divided by R ER. Okay, is this fine? So VR is equal to Q divided by R, and if I put instead of R, I put it as square root of x square plus y square. Now, what happens at y is equal to 0? V sub R is equal to V of x, and this is equal to Q upon x. Now, can anyone tell me what is capital U of x for this potential flow?
So Q by X.
Is the same thing. So what we have found is, because this is the potential flow velocity at the wall. So now in this flow, if I have a potential flow like this, capital U of X is equal to Q by X, and it is not equal to constant. But this is because the flow at infinity is not uniform. In fact, in this case, flow at infinity is 0. As you go to infinity, there will be no effect left. So in this flow, in this boundary layer flow, past the flat plate, capital U of X is not equal to constant, but equal to Q upon X. And so the pressure gradient here on the wall which is dP by dx. So this term, if we calculate U du by dx, this will be equal to Q over X times minus Q upon X square, which is equal to minus Q square upon X cube. So the pressure should increase. Minus sign की गलती है क्या? Let me just x goes to. Okay, so this is U du by dx. So this is equal to minus 1 over rho dP by dx. So this is just to illustrate. By this example, I thought I have clearly illustrated. Is that fine?
Yes, sir.
So
Yes,
by
sir.
nomenclature, the wall is taken as the x direction. So even if we have a vertical wall, if we are doing boundary analysis, we will take x along the wall, and y will be the component perpendicular to the wall. And you may have to change u and v accordingly. Okay? X by definition is always taken along the wall when we talk of boundary. So in this methodology. Okay. So now let's try to see, can we find solution of the boundary layer equation? And you realize that when we are trying to do this, this was a lot of this theory, people were trying to still not resort to CFD. They were trying to find analytical solutions. They could not find analytical solutions of the full Navier-Stokes equations for many cases. So then they said, okay, is it possible to resolve and get some sort of solutions of boundary layer equations? And what one finds is if capital U of X is of the form A times X to the power of n m, then we can find a similarity solution for the boundary layer equations. Of course, capital U may have any form, but if it is a polynomial in X, then we can find a similarity solution. And what does this mean? That is, if we put eta is equal to y times x to the power of a and feed this in the boundary layer equations and the boundary conditions, then the PDE u du by dx plus v du by dy is equal to capital U du by dx plus nu d2u by dy square is converted to an OD. And one of the first person to do this was Blasius. Blasius did this for m is equal to 0, that is for uniform flow past a flat plate, or Z0 pressure gradient boundary layer. And here he showed this variable will be equal to eta is equal to y bar root x. And then this is one of the, what Blasius got was the exact solution. We also have some approximate methods of solving the boundary layer equations. Now, but one more thing before I end the class today, we will look at some of these different types of boundary layer thickness and approximate methods in the next class. One of the ways, if we have flow past a wall and do not have potential flow solution, then sometimes what people do is on the wall, you find P of X experimentally. So at different X locations, X1, X2, Xn, find or measure P of P at these locations. Experimentally, we find P of Xi. And from here, we can calculate dP by dx. And this can be fed in the boundary layer equation instead of u du by dx. And possibly one will have to do this if there is a porous plate or something like this. If we cannot find capital U, or if we cannot find the potential flow solution, then we can find P of Xi from experiments and then use these to solve the boundary layer equation. Okay?
Okay, sir.
I have partially answered that question of the porous wall. By
Yes,
this
sir.
technique, one can do this. So, so that is how one does this. So, but keep in mind, there are two restrictions when we talk of boundary layer equation. One is the Reynolds number has to be very large, and the second one is that the body, the radius of curvature of the body has to be large enough. If these two conditions are met, then we can use the boundary layer equations, which we have done for any body, not just a flat wall. But of course, you will need to know either capital dP by dx or du by dx. Okay. So with this, I will end. I've started grading. Are the grades visible to you, or have I put a have I made it invisible? I don't know. I don't know if I put that option on. I've graded the first two questions of the minors. I will grade the third and fourth also.